Perfect. All right, so our first speaker this afternoon is Giselle Jimenez, who joins us from CSU San Bernardino. She's been working this summer with Ivanna, and she'll tell us about her project, modeling the chemical evolution of Andromeda's stellar halo. Go ahead whenever you're ready.
Hi, everyone. Thank you for joining us this afternoon. And I'm really excited to be discussing the research I've been working with this summer with my mentor, Ivanna. To start off, I'll be going over a brief overview of my background about the stellar halo, chemical abundances, and chempi, as well as discussing my methods with the M31 data, and finally discussing my findings with the chemical evolution model and my current and future work. Why is modeling the chemical evolution of Andromeda stellar halo interesting? Other than it providing us with an insight on the history of the gas and star formation for stellar populations in the stellar halo of Andromeda, this will also be the first type of modeling for the Andromeda galaxy and outside the Milky Way system. So the first type of alpha to iron and iron abundance modeling to look at the chemical evolution tracks. And this can also be a stepping stone to learning the history of the universe, since the Andromeda galaxy is the farthest distance that we can see with our current equipment that can give us a high enough quality of the alpha to iron abundance measurements for one star. So hopefully in the future, we can see farther beyond the Andromeda galaxy and be able to get good quality of alpha to iron measurements for more stars. So a stellar halo is composed of stars that orbit around the center of a galaxy at various speeds and distances. These differ from the stars in the disk of the galaxy, since those do orbit around the center of the galaxy at fixed speeds and distances. So here we have an image from Gilbert et al.'s 2019 paper showing Andromeda stellar halo. So we have the Andromeda galaxy in the center here, and the stellar halo is depicted by the white outline. So Andromeda stellar halo is relatively large. It's roughly 150 kiloparsecs wide. And we can also see the various spectroscopic fields in the stellar halo, which are from the Keck Deimos telescope. So each spectroscopic field spans a wide range of the stellar halo and targets hundreds of stars. One distinct feature in the halo is depicted by the white arrow here. So this is the GSS, also known as the giant stellar stream, a smaller dwarf galaxy that was being accreted into the Andromeda galaxy was partially destroyed by the tidal forces in Andromeda, resulting in this big stream of stars here. So what we can do is study the chemical abundances of stars from the various spectroscopic fields and apply chemical evolution models to them to learn about their history. Chemical abundances. So here I have a plot from my mentor Ivanna's 2019 paper showing the spectra of a red giant star in the Milky Way globular cluster from the Deimos spectrum. So I am showing a spectra of a red giant star from the Milky Way, since the data is much higher in quality than what we work with in M31. But what I'm showing here is a plot of the normalized flux with respect to wavelength in angstroms. The black line is the spectra of the star. And by observing the spectra's dips, we can determine which elements are present in the star's light. So there are various wavelength regions in 3 different colors. We have pink, blue, and green, representing magnesium, calcium, and silicon. And these represent the different elements that can be detected at those wavelengths. So at various dips in the spectra, for example, the 5200 wavelength region, magnesium is present there, and we see a dip in the spectra, which can tell us that element is present in the star's light, as well as the 8500 wavelength region. Calcium is present here. We see 2 very distinct dips in the spectra that tell us calcium is also present in the star's light. So the main takeaway is that we can use these wavelength regions that are highlighted to constrain the chemical abundances using spectral synthesis and then apply the chemical evolution models to learn about their history of the stars. So these stars I am working with form from two different stellar events, core collapse supernovae and type 1a supernovae. Alpha elements are produced in core collapse supernovae such as calcium, magnesium, and silicon. Those are the three elements that I'll also be tracking in my evolution model. And these elements are released rapidly in evolutionary history compared to iron, which is produced in type 1a supernovae. Iron is released more slowly in evolutionary history since it does need a white. Type 1a supernovae do need a white dwarf to produce iron. And iron can also be used as a factor of time to show the time scale between the core collapse supernovae and the type 1a supernovae. Which brings me to chemical evolution modeling with ChemPy. I have been using the ChemPy Python package to produce chemical evolution models for Andromeda. So how ChemPy works is that it's specified by various parameters describing galaxy evolution, such as star formation history, initial mass function, and gas inflow rate. And it produces observable predictions for those parameters. I have an example on the right. So here I have a plot of the alpha abundance tracks with respect to iron. So I have 3 abundance tracks of magnesium, calcium, and silicon. And as you can see, we have a very high alpha to iron abundance ratio throughout the evolution of the galaxy. And that tells us that core collapse supernovae were dominating throughout the evolutionary history of Andromeda. And towards the end, we see a decline in these alpha abundance ratios, which can tell us that the type 1a supernovae started dominating over the core collapse. So what this just shows us is the timescale between the core collapse and the type 1a supernovae throughout the evolution of the galaxy. So the 2 main questions I've been trying to answer are, how did Andromeda and its stellar halo and tidal stream form? And how do we apply chemical evolution models to learn about M31's history? So what I've done so far is that I've obtained the M31 data from the elemental abundances and M31 survey obtained from the Keck-2 telescope and the Deimos spectrum. And I have separated that data into the smooth stellar halo and intact tidal debris components using the substructure probability. So the plot on the right is the metallicity versus the heliocentric velocity of all the stars in the stellar halo. And the color bar here is the substructure probability, which can tell us which stars have a higher probability of belonging from the intact tidal debris. So with the higher probability, the more yellow in color, and the lower probability, the more purple in color. And that can also tell us that if it has a lower probability of belonging from the intact tidal debris, it has a higher probability of belonging from the smooth stellar halo. So the substructure probability is derived from the heliocentric velocity, and around at the negative 300 kilometers per second range, this is actually the systemic velocity of the Andromeda galaxy. So this line here is the center of the heliocentric velocity of the stellar halo. So what I've done, I have separated the data into the smooth stellar halo and intact tidal debris components. We have the smooth stellar halo on the left and the intact tidal debris on the right. And I have also produced an average alpha element ratio track from the 3 elements that I have tracked before in my chemical evolution model. So I made an average of those 3 and plotted it against the M31 data. So this is just a preliminary comparison of the alpha track to the data. We can't make conclusions now since we do have to differ the parameters of the alpha track to best fit the data. Which brings me to my current and future work. So I am currently producing mock chemical abundance data from the chemical evolution tracks according to the age distribution of various fields in M31. And the age distribution was obtained from the Hubble Space Telescope. So the data that we sampled is not fit to a certain age distribution, and I will use a combined age distribution from the various fields for that data. And for my future work, I will be varying the assumptions of the model to compare by I-fit, and also plot the best fit chemical evolution track against the M31 data. Thank you all for listening to my talk, and I will gladly take any questions.
All right, very nice, Giselle. Do we have questions for her? So I have one question. Oh, Alex has a question. Go ahead, Alex.
Giselle, I had a question about, so I guess, are the tracks, do you expect the tracks to be different for modeling the substructure and the halo in terms of what is what's going to be the best one?
For the, do I expect the ratio to be different when I compare them to the data?
Yeah.
I really wasn't sure. We weren't sure what to expect since this was the first type of modeling we've done with the data. But what I'm trying to do now is to vary the parameters of the data to try to fit it best to the abundance of the stars.
I see. Awesome. Thank you.
Thank you.
All right, perfect. And I was curious on that on your last slide, Giselle, is the actual age distribution of red giant stars in Andromeda?
So this is one of the age
of the spectroscopic fields? Yeah,
one of the age distributions of one of the fields in Andromeda.
Okay, very cool. So you're going to be looking at a handful of those and sort of trying to input those to the model. That's super interesting. All right, wonderful. Anna, do you have a question?
I do. It's really nice work, and it's amazing how many abundances you have. And so,
Anna, I can't quite hear you. I don't know if other people are having difficulty or not, but. Anna's going to type. Okay. Okay, so Anna says, with the abundances you have, do you think it would be possible to improve the substructure probability? So use the abundances to make some prediction about which stars belong to which structure.
That's a good question. I am not so sure. I think it would be possible to improve the substructure probability, but I haven't thought about doing that yet. So that I will think about that and talk to my mentor about it as well.
Perfect. All right, thank you so much.